So this ladder looks very stable, but it's actually on the verge of slipping. So this question is how much friction is needed to keep it in place. And we're going to solve this step by step, so that's by the end of the video you will understand fully what to do if you come across questions like this. Now we have a ladder that is 4 meters long, so I'll just input these details as we go along. So we know the ladder is 4 meters long and it weighs 1000 newtons. So that's actually given as a force. So this here, its weight is given as a force. So the ladder weighs 1000 newtons. So for W, I'm just going to write that as 1000 newtons. Now it's resting against a smooth wall and a rough ground. And there is also a 750 Newton load acting 1 meter from the bottom. So that could be, let's say, a person or something like that. So I'll just add that 750 right here. So that's 750 Newton acting 1 meter from the bottom. Now, before we do anything, we usually need to draw a free body diagram, but this is mostly done because I didn't want to waste too much time doing it. So I'll just explain what you're looking at. So at the top of the ladder, the wall is smooth, and what this means is there is no friction. So because of that, we only have one horizontal reaction force, and I'm going to just label this force as NB because it's a normal reaction. A normal reaction simply means the reaction is perpendicular to the surface that it's reacting against. And then at the bottom of the ladder now, so on the ground, we have two forces. So we have another normal reaction that's acting upward, and I'm going to label this as our NA. So that normal reaction is acting upward, and we have a friction force acting horizontally. So this is a force, FA, that's acting horizontally. Now, if you think about it, the direction of the friction, the ladder would try to slide away from the wall. So if you're drawing your free body diagram, that's why the friction must act towards the wall to resist that motion. So in terms of the ladder's weight now, where you would add this on your free body diagram, that would be halfway up the ladder because it's going to act at the center. So similar to how we treat UDL. So I'll just add this somewhere here as 1000 newtons. And I've already added that 150 Newton that acts 1 meter from the bottom. And one more key point is that the ladder is on the point of slipping. We have to remember that, which means friction is at its maximum value. So we're going to write this equation then, which says FA, which we have at the bottom there, is going to equal to mu, that's our coefficient of friction, multiplied by our normal reaction A. Now let's start solving the problem because we have analyzed it, drawn our free body diagram, and we're going to start solving. So the ladder is not moving up or down at this point. That's the first thing we need to remember before we start solving. So the total vertical force must be 0. And if we look back on our diagram and just look at the vertical forces, we have NA, we have that 750 newtons, and we have that 1000 newtons. So if all of these must be 0, what we're going to do is take upward force to be positive. So that means NA is going to be our positive force here. And we're going to take 1000 because that's going the opposite direction, that's going downward. And we're going to take also 750. And all of that should be equal to 0. So if we were to solve this then, NA would be equal to 1750 newtons. So that's our normal reaction there at the ground, which is pushing up. So just before we start to look at the horizontal forces, I am now available for one-to-one sessions, so if you'd like any support in terms of exams, coursework, assignments, that sort of thing, then check the link in the description and book a one-to-one session. So back to the problem then. So again, the ladder is not moving left or right. So similar to how it wasn't moving up or down, it's not moving left or right. So we have this analyzed as a static problem. So the total horizontal force then must be 0 because we're claiming the ladder is in equilibrium. So I'm going to set out another set of equations now where the total horizontal forces should be equal to 0. So here we have only two horizontal forces. We have NB and we have FA. So if one direction were to be positive, the other were to be negative, let's say we would have NB and take FA should be equal to 0, or the other way around is fine. But what we would end up with here is that NB should actually be equal to FA because they are the only two horizontal forces that we have. And this is very important because with this approach, if we find NB, it means we automatically know the friction force. So get what you need from the screen here. I'm just going to erase this to make some space, and I'll make a note of the figures that we have so far. So now for the key step here, which is we're going to take the moment about the bottom right here at this point. We're going to take the moment about that point. And why we're using the bottom, that's because we have two of our forces acting at that point. So if we were to take the moment about that point, those two forces will have no effect on the system. So let's start then. Let's start with the 750 newtons. And this force acts 1 meter along the ladder. And because it's a vertical force, we need the horizontal distance. So I'll just write this so it's clear what we're doing. So it's moment from the 750 newton. So using the angle 60 degrees, this would give us just 1 cos 60 degrees. And in the calculator, 60 degrees is 0.5. So 0.5 times 1, that gives us 0.5 meters. And that 0.5 meter is along the horizontal. Very important to note. So that first moment then will be 750 multiplied by 0.5. That gives us 375 newtons. And it's Newton meters for moment. Right, so now we're going to take the moment from the ladder, the weight of the ladder. So let's do that. So moment from the 1000 newtons. So it's the same process, really. So we know that this is 2 meters up the ladder. So this is just going to be 2 cos 60. And this will give us the horizontal distance of 1 meter. Cos 60 is 0.5. So I'll just draw a dotted line for this one so you can see what we're calculating in terms of the force and the perpendicular distance. And I'll trace this as a purple line. So it's this here, this purple dotted line. So that force there, that's the 1000 newton. And we're multiplying it by that horizontal distance there, which is what we just calculated to get to be 1 meter. So when we do that now, it's 1000 multiplied by 1 for the moment, and this gives us 1000 Newton meters. Okay, so that should be enough. So now this time we're going to take the moment from the wall reaction, so that's the NB. So we're going to now take the moment from NB. So that's the moment from NB we're going to do now, and that's the wall reaction. So this force was the horizontal, because the wall reaction only had one force, which is that horizontal reaction. And it's going to be the full height or length of the ladder. So this will just simply be 4 sin 60 for the horizontal distance. And this gives us 3.5 I'll just write it to 3 decimal places, 3.464. So the moment now for this is just going to be our NB multiplied by 3.464. NB at this point is an unknown force, but just for now. So this now is where we solve the moment equation. So we're going to take the moment about the bottom, everything that we have so far, and we should have all of this bit be equal to NB. So this is taking the moment about the bottom, and I wanted to chunk it previously so you could follow step by step what's happening really. So this would be our first bit, which was the 750 times 0.5. That would be rotating in one direction. And then we have this 1000 times by 1, which is rotating in the same direction. And then we have NB times by the 3.464, which is rotating in a different direction. And I will go back to the diagram now just so that you understand why we have these two on one side and this here on one side. So let me go back to the diagram just to show you that bit. Okay, so I've got the urge to sort of erase this so you can clearly see, but I'll do my best to do it with the annotations on screen. I'll use a blue color since I've not got any blue on there already. So we're taking the moment about this point right there. And that 750, when we try to rotate, is going in this direction. So you can see that, I'm sure. The 1000, which is the weight of the ladder, is going in that same direction right there. But then the NB is going in the opposite direction. So these two, let's say, they're going clockwise, but the NB is going counterclockwise. So when we sum these, we can say clockwise moment should be equal to counterclockwise moment. So that's why on one side we have the 1000 times 1 and the 750 times the other value that we got there. So now that you understand that bit, we can now solve here. So this would give us, we got 375 up top, so that would give us 1000. That would give us 1375 equals 3.464 NB. So then, therefore, if we were to just divide the 1375 by 3.464, we would get what NB is. So NB 396.9 newtons. So that's NB. And since we have established before that FA is equal to NB because they are the only two horizontal forces and they're acting in opposite directions, so then we can just simply say that FA is also 396.9 newtons. So that gives us FA. Now with FA found, we can now simply rewrite our equation that we had from the start. It's probably too late to ask, but if you're still here, I would appreciate if you subscribe to the channel if you haven't done so already, and just give the video a thumbs up if you find it useful. So let's do the substitutions now so we find what the friction here is, and I'll explain to you what these values represent. So we have FA as 396.9, and that's going to be equal to our coefficient of friction multiplied by the 1750 that we got for NA. So to get the coefficient of friction, we would just simply do 396.9 divided by 1750, and that gives us 0.227. I'll keep to 3 decimal places. So this 0.227, it tells us that this is the minimum friction needed to keep the ladder from slipping. So if the surface can provide more than this, then the ladder will stay in place. but if it provides less, then the ladder will definitely slip. Now we're going to build this up as a series, so in the next video we're going to look at another variation of this type question, and I will see you in the next video that will be shown right here.